So, we recalled the necessity of certain measurements of solar radiation, which may be on a hourly time scale, which we have already discussed, from where you construct or calculate the daily values, from which you may come out with various averages. It could be average hourly value or average daily value or average monthly value or even yearly values. Most of the time it is the global and diffuse components measured. Direct solar radiation component is measured for check. So, essentially that means once in a while you can go through that, not that it is prevented to measure the direct component radiation. Simply when once you have got, typically you focus the instrument towards the sun, any small error in focusing towards the sun will lead to a large error. In fact, it may go out of the range of the sun. Consequently, a lot of care has to be exercised in using the direct radiation measuring instruments, not only in tracking and even in seeing that the tracking is well maintained. So, I shall show you some pictures of the instruments. You will have a better idea of how they work, and all the details or cross sections I cannot show, because the instruments are working, they could not be broken, and these are manufactured by National Instruments in Calcutta in India. And right now I believe the company is not working anymore. However, these instruments were bought some time back. First you will see a pyranometer, and you will see on the glass bowl in the middle there are two concentric hemispheres with that Parson black at the middle, and this is polished. Under that surface is a thermopile, which is basically thermocouples in series, which will produce a higher millivolt output for a given radiation input. As I said, typically they are around 100 to 200 1 millivolt for about 100 to 200 watts per meter square. This is another view, and you must be wondering why so far I have not mentioned about the surrounding disk, and this surrounding disk shall have the no other radiation being reflected onto the sensor. So, that it will be measuring only the total radiation or global radiation falling onto the sensor. Now, this is to measure the diffuse radiation, and basically you can see that the instrument is the same, but there is a large ring which you can see, and that ring shadows the sensor, which is the bowl over here. Now, you will also find an arrangement that it is inclined, and the inclination can be changed by, there are two nuts on which this ring is mounted. You can see like this, and that can be turned depending upon the location of the sun. In another view, you will find a scale. For example, it is 0 and it goes to 23 degrees on one side and another 23 degrees, and that slide can move to the positive side or the negative side of the angle. Depending upon the declination of the day, you move that, and then you will adjust to shade the sun that is falling, so that the sensor is shaded from the sun's direct rays. So, thereby it will measure only the diffuse radiation. Now, this is a short tube pyroheliometer, and as I said that you can't see the details. At the bottom of that long tube, you have a sensor which gets heated due to the solar radiation, and that cap, when it is removed, is directed towards the sun, and then the rays falling on the sensor will heat that. This is just to show you the difference between the long and short tube pyroheliometers. The long one is uncovered, that seal is removed through which the solar radiation enters, and the long tube will have a lesser subtended angle and measures the radiation emanating from the sun only, and the short tube one will have a higher subtended angle. Consequently, it measures certain amount of radiation that is also coming from around and surrounding the sun. So, this is an angstrom pyroheliometer. Basically, the sensor mechanism is different, in the sense it uses a null detecting system, like if you are in electrical technology post office box, if I remember right my undergraduate electrical engineering, you try to balance so that the current passing through a particular circuit is 0, thereby giving you a measurement of the voltage generated or the power that is consumed. Now, we come to your dependable sunshine recorder. It does not require any power, and this is a view. Of course, there is a lot of reflection, but this is a better view, and there you will find that black strip at the bottom of this glass bowl, and you see onto the right a little bit of charred portion, which I am also showing it in an enlarged view somewhere in this area. You will find a black charred portion. So, if you measure all the length of this charred portion, that will give you the number of hours of bright sunshine, and these strips basically you will have about 3 lengths to suit summer to winter variation, because though you may not feel much of a difference in lower latitudes, as you go to higher latitudes the day length can be as much as something like 15 hours in summer, or to maybe 6-7 hours in winter. So, you will find the length needed in summer will be much longer than the length needed in winter months. Now, doing all this, what is the use and how is this used? So, Page is a early researcher in the area of solar energy. At that point of time, the measurements available were small. This 4 is the reference. If you look at your notes, you will find out the details. We were talking about the terrestrial radiation by the extraterrestrial radiation. This is linearly related through a constant A plus B to n B upon n S. N B is the number of bright sunshine hours obtained from the sunshine recorder, and N S is the possible number of sunshine hours, which we know equal to twice omega s by 15, which we have derived the formula in the other class, where omega s is so called sunset hour angle, which is related to the latitude of the location and the declination. And later on, this is applied to the monthly average daily value, as in fact, these constants need not be the same, N b bar, N s bar, where N b bar is the average of bright sunshine hours and N s bar is twice omega s by 15, where now omega s is cos inverse minus tan phi tan delta mean. We have got recommended mean declinations for each month. So, we use that, and this need not only be the average of N b bar and N s bar, it could be total number of bright sunshine hours by the total number of possible sunshine hours. Even then it will be equal to the ratio of the averages. And here I had to add a note, this angstrom type of relation, originally angstrom expressed in terms of clear sky radiation, and you can see the book by Duff and Beckman for the details. In other words, it is instead of h bar upon h 0 bar, it is h bar upon h clear sky. There is a certain vagueness in defining clear sky, because that needs to be estimated depending upon certain features of the atmosphere. So, now where do we stand? We have a method of estimating h or h bar, and if we make use of detailed instruments like pyranometers, we may have I and I d, and hence I b equal to I minus I d. So, most of the time the time scale is about 1 hour, and few measurements are available at smaller intervals. That is, the reason is, for a well distributed day, we have seen the solar spectrum to be something like this, up to 4 microns, and if you take a 1 hour interval, unless there is a sudden cloud cover or rain, the chances are you may not have such a wild fluctuation. So, if you take this is approximated by a straight line, or you can make it an equivalent rectangle, and if you have 1 hour radiation by a known distribution like it's linear or parabolic, you can distribute it into quarter hours or half an hours, though one has to think about whether that accuracy is needed or called for, depending upon the model that you employ to estimate the performance of a solar collector or a solar energy device system in general. So, now if you do not have all the details, you may have only h y bar. I am making the broadest possibility, or you may have, that is the yearly average radiation, from which you have got h bar for each month. M 1 to 12, or you may have h I is equal to 1 to 30 or 31 for each m. Then of course, you may have got I for each day and I d for each day. I do not keep on saying I b can be estimated from these two. So, if you have got this data, you can go to H I, you can go to H m bar and you can go to H y bar. But though it is uncommon, when you calculate from H bar, you can total up and find out H y bar. If I start with a something like monthly average radiation, can I come to distribution of I? So, this is at different points of time, the correlations have been coming in 1960, Leon Jordan, and as late as 90, 2000, they are continuing to come better and better relations than what they were existing. In retrospect, getting the detail from known broad averages, we may call it the latest terminology synthetic data generation. You may wonder what is synthetic data generation, and in fact, some people get upset with this term. Nevertheless, this has got certain attributes. The data generated from no matter what is the source, the monthly average or the yearly average, it will mimic actual data and produce reasonable long term results. What we mean is, if you want to predict the performance of a solar energy system for a day, for a particular hour, it may not be highly accurate, but for a month, okay. For a year, it may be even more okay. So, since our economics is likely to be based upon year, and if it mimics the month distinction, let us say between winter and summer reasonably well, our job is done. It is not essential how much is exactly produced on January 1, 2nd, 3rd, 4th like that, and if I can have a January average, it is good enough, because in any case next year it is not going to be reproduced, and even if you use the actual data, that actual data also belongs to some year or average of few years. So, that scheme again towards the end of these lectures, we will come to that in detail, but at the same time I just gave an introduction to whatever classically available can be considered as part of a synthetic data generation scheme. Original diffuse fraction correlations. Orgel and Hollands expressed the ratio of diffuse radiation to the global radiation as a function of hourly clearness index, which you may recall is equal to I upon I 0, which we have discussed in detail. Of course, this relation I will not reproduce here. I d by I is 1 minus 0.249 k T depending upon the value of the k T. Similarly, another relation for k T between 0.35 and 0.75, and you have a 0.177 for k t greater than 0.1. So, if you try to plot this, you will get some result like this. These are the equations, but if you plot the data, there will be a lot of scatter. Now, that scatter may be due to k t only being not the correlating parameter, or it may be some sort of measurement error, and most scientific reason is that the climate can be little bit erratic. Consequently, one may not be able to correlate with a single variable. Now, you understand why we spend considerable time in introducing this so called clearness index. Now, you will see that this I d by I is a function of k t, reasonably well represented, and that correlation has been given by Orgel and Hallands. Of course, you will ask what is the use of it. The use of it is, if I is known, in other words, or only I is measured, we can find I d. This is one is, that means the number of measurements that we are trying to make are reduced, but at the cost of course, some accuracy. But later on we will see some 10%, 15% difference in the estimated I d value may or may not make much difference. Whether it will make lot of difference or not, we will find out from the relevant formula that we will be seeing in a little while. Similarly, Collares, Pereira and Robel they proposed a relation, similar ratio for the daily H d by H t. Again you can see at the screen where there are 4 relations depending upon the value of clearness index in the range of 0.17, in the range of 0.75 and up to 0.8, and k t greater than 0.8, and H d by H is a simple constant 0.2 for k t greater than or equal to 0.8. Mind you, this is the daily clearness index, and that we know is h upon h 0. So, this means the number of days available with capital K T greater than 0.8 are far and few. Consequently, one may not be able to find much of an accuracy and globally use a value of 0.2. So, like the hourly clearness index, this daily clearness index also has a role in predicting the daily diffuse fraction values, which again translates into, if we know H d can be predicted. Of course, you should realize that there will be a difference from an actual measurement and a correlation that is being used. That means, a consequence of only I gives us only H. So, I can go through I d root, keep on predicting I d from the values of I, or then get H d as a summation of I d, or use H and get H d. So, now there may be a difference between these two. are these two equal? This could be somebody can investigate this and find out which is a better one to use. So, you can also see the previous correlation has got 4 parts, and the next correlation by Collares, Pereira and Ravel gives the monthly average daily diffuse fraction as one single equation, which again you can see on the screen, right. And now, this is a function of k T bar and omega s. If you see this, December and June, omega s can widely vary. Consequently, if you have a large omega s like in summer, then h d by h value will be, or you can calculate, I think it will be lower, and if you have a small omega s, you may have a higher diffuse fraction. Okay? So, you can just check up for a value of omega s, let us take 120, omega s 80, and find out what is h d bar by h bar. Then, as a food for thought, you can try to explain on a physical basis why h d by h is larger or smaller if you have a higher or smaller omega s. Also, again some sort of a task for you to set you thinking. If you have got a function of k T and omega s, we know that path length depends on season, right. Also, your angle theta z depends on the day. So, I just propose your h d bar by h bar may be a function of k T, omega s and theta z bar. How I define this average angle of incidence for a horizontal surface, I do not have a ready answer, but somebody can think about it. So, now again I can find out the diffuse fraction for the monthly average day given the monthly average global, for similarly for the day and similarly for the hourly values. Then originally Liu and Jordan they proposed a ratio R d which is I d upon h d. Please note that this is the ratio of hourly diffuse radiation to the corresponding daily diffuse radiation, right. And this is simply given by, I will write, this is a smaller equation, there is a purpose. I think I shall move this a bit here. So, you can see that relation. Now, typically my I is between omega 1 and omega 2, I 0 also the same. Consequently, I d also between omega 1 and omega 2. But now, R d is a function of omega, a single value of omega, not an interval. So, if omega is the midpoint of the particular hour under consideration, my ratio of I d by H d will be for the hour centered around omega equal to omega 1 plus omega 2 by 2. In other words, it is a continuous function, and if you give a value of 32, it will give you between 25.5 to 39.5 degrees. So, it is not necessarily exactly 1 hour from noon etcetera, but depending upon the value of omega give, it is expected to give you an hourly value. However, since all other data will be in terms of the solar time, we will calculate at the midpoints of the corresponding solar hours. And one more comment is in order. You calculate or express I 0 by H 0, which is G 0 at omega into 3600, because we are calculating the midpoint by H 0. This will be identically equal to expression, not numerical values, not necessarily the numerical values. This cos omega minus cos omega s by sin omega s minus 2 pi omega s etcetera, that is derived, just one can take extraterrestrial radiation ratio, it will be equal to I d by H d. This at one point of time was a bit surprising. Later on, certain issues were resolved. Now, you will also find that R d purely geometric factor. In other words, no matter what your clearness index is, and if you are having a particular day length and omega, you will have exactly the same ratio. So, this is something that makes you feel uncomfortable. However, more things will follow little later. Again, Coleris, Pereira and Rabe expressed R t, which is the ratio of hourly global radiation to the daily global radiation. It is, I will write it for simplicity as R d into a plus b cos omega, where a and b are given in terms of certain constants and the sunset hour angle. So, interestingly, this is also geometric, but these a and b were correlated with the data of many locations. In other words, if you attenuate this theoretical ratio sort of by a factor changed by omega s with these constants, you will get a expected distribution of I by h. Now, you can expect R d in general has a higher error and R t is typically about 4% RMS. You have to understand the root mean square error meaning, or that is actual errors can be larger, but that is sort of an average error. Whatever I was mentioning, I left it as an exercise over here. Prove that R d also equals to the ratio of hourly extraterrestrial radiation on a horizontal surface to the daily extraterrestrial radiation on a horizontal surface, that is I 0 by H 0. I gave you sufficient hint, you can just verify and make sure that what I said is right. So, later on work at Energy Lab at Kharagpur has taken into certain climatic features in developing correlations for RT and RD, including asymmetry. A word about asymmetry, because that is a very advanced topic, less understood, not yet possible to really formalize it. Generally, morning, that is forenoon radiation is not equal to afternoon radiation. If you look at these correlations, it looks like solar radiation distribution is symmetric around solar noon, whereas in reality the morning may be higher than the afternoon radiation and vice versa. There is no specific geometric bias, but both kinds of locations are observed. It has got to do with a lot of meteorology, which is responsible for the formation of orographic clouds, which sometimes will produce more diffuse radiation or more cloud cover, affecting the radiation in the forenoon part or in the afternoon part. Now, we will go to what is meant by distribution of clearness indices. So, based upon the North American locations, again Liu and Jordan, they developed curves for clearness index versus cumulative frequency which will vary between 0 to 1. I will explain in a minute what is meant by cumulative frequency. This is nothing but the fraction of the time that occurs below a certain specified clearness index. So, translated in simple terms, if you consider a monthly average daily clearness index of kT bar, there are 30 or 31 for a given kT bar, you have got 30 or 31 kTs. Okay. Now, we find 17 kTs less than 0.72. So, the fraction is 17 by 30, which is about 0.7. So, my cumulative frequency is 0.7 if your capital KT is 0.72. That means 70% of the days will have a clearness index less than 0.72. This you can more easily understand in terms of the percentile of the marks. If you have got 20 or 30 students and the minimum is let us say 21% and maximum is 76%, and if you find out how many people got below 22, 24, 25 like that compared to the total number of students will be the cumulative frequency of occurrence. So, the utility is if you have a generalized distribution of kT versus this cumulative frequency, you can generate all the 30 values. In other words, this is f, this is capital K T, it is one curve, this may be belonging to K T bar is equal to 0.5, obviously this will be 1, this may be slightly less than 1, because this K T 0.9 or 0.8 will be a very high value. So, if I choose a 0.4 to mark and go this may be let us say 38. We can say that 42% of the time the clearness index is less than 0.38. Okay. So, this many days or this much fraction of the time will have a clearness index less than this value of 0.38. So, if we discretize it into 30 parts, I will have 30 KTs. Okay. This is of course, in general can be told in terms of the fraction of time, but for the ease of understanding, for easy understanding, I just made it a each day, because that is the way the daily clearness indices were developed. So, this is redrawn figure of Leon Jordan. You will find that interesting features. If you take a low average clearness index of 0.3 and then a higher clearness index of 0.7, sorry, it does not group down, it should go up 0.7, you will find that there are more number of values towards the lower end and there are more number of values towards the higher end. Once again, you can easily understand, if the average number of marks in a class is 92%, many students must be having a higher percentage, and if the average is 38%, many students must be having lower numbers. So, this is the trend that can be expected, and what you will find is that minimum K T at 0 f is quite a bit varying between like something like 0.0 to 0.3, though not so much the higher end of 0.9, which is also understandable. If the average is low or high, the minimum value of the clearness index can vary a lot, whereas the maximum there may be a single day with a 0.8 or 0.9. So, they coincide. So, these curves have been found to be valid for hourly indices also. In other words, you just have the same set of curves f, you make it small k t here and this is small k t bar. So, for a given numerically equal hourly average clearness index to the daily average, monthly average of daily clearness index, you have the same frequency distribution. This comes as a bit surprise and could further be examined. The reason is, if you have the daily values and I define the swing as first thing I can think of this swing can be different for different locations and even different seasons. For example, if you consider a tropical climate like Chennai for example, and more or less all the days are uniform. So, this swing will be smaller, and whereas if you consider a similar average value, but at a higher latitude, there may be one cold day, there may be a rainy day, the variation between maximum to the minimum is likely to be different. This much can be said from location to location. Similarly, if we have hourly KT maximum minus hourly KT minimum given KT bar for numerically equal hourly average and daily average values. The swing in the hourly values I can expect to be little higher than the swing in the your daily values. So, these features can still be considered and examined. And we have developed some modified distributions, and which will be discussed as a part of advanced topics, which may be skipped for a undergraduate portion, and then we will go ahead with these things for the whatever textbook are directly available. So, now I shall go to utilizing all the correlations which we have written as a part of also synthetic data generation. We may not have all the missing links, but some links which we use. So, I shall show from the sort of a flow chart. You start with H bar. On the right hand side, I will be showing that you can calculate what is H 0 bar and KT bar. From there, you can calculate HD bar, diffuse part, okay, and also of course, HP bar if you want. How? We have the correlation for HD bar by H bar. So, the input I can show it like this, HD bar by H bar is a function of KT bar. Now, I use RT and RD correlations for the average day. In fact, these correlations we can expect that these RT and RD correlations to yield better accuracy when applied for the average day than for a single day, because the averages will be smoothing out the hourly values and it will generate a pretty good distribution, and that is what you have. So, if I use RT and RD correlations, then I can have what we defined earlier, I bar for all hours and then ID bar for all hours. Okay. So, let me recapitulate. I used H bar, obtained H d bar, then used R t, R d, got I bar and I d bar. In other words, from the given simple monthly average daily value, we could generate the hourly average, of course, hourly values of global radiation and the diffuse radiation, right. When once we know the formula, we will appreciate even more why these things become necessary and why we are trying to talk about more of I and I d and trying to get it from H or H bar and I. Similarly, from H bar, since I know K T bar, go to Leon Jordan F versus K T or capital K T curves, and generate K T. So, from this calculate 30 H values. When once you have now apply R t correlation, which will have I values for all 30 days. So, now I have one path for each H. I can get a H d by applying Kollares-Pereira-Robles correlation for the day, not the monthly average, and apply R d for each day. So, we have I d days. So, in summary, we should be able to say, given the monthly average clearness index or monthly average daily radiation, we can make use of Leon Jordan's cumulative frequency distribution curves and apply R t and R d correlations for individual days or for the monthly average day and generate the needed hourly values for the 30 days. So, in this process, we can't assign a sequence what is January 1 or January 2, but we can generate a sequence of 30 numbers, which we may able to randomize and then use for our simulation studies.